All right, so this is lesson 7, investigating the graphs, part 1. So this is again a review. We've already written this down a couple times, but let's see here. Zeros of the function, x-intercepts of the graph, and roots of the equation are all the same numbers. Again, why we have 3 different terms for the same thing? Who knows? Math. So the unique factorization theorem states that every polynomial of function degree n greater than or equal to 1, so that is not a constant function, can be written as a product of a leading coefficient, some constant value c, and then all these different linear factors. So this is 2 important points. Every polynomial can be written as a product of its factors with a leading coefficient, and every polynomial function has the same number of factors as its degree. Sometimes their factors might be real or complex. Sometimes they may or may not have x-intercepts that we can see on our graph. We'll see all of those. So this thing is shown, and it has integer, which is that integral, integer values for all of its zeros. So its 0 is -2, +1, +3. So -2, 1, and 3. The factors will be the factors that match that 0. So the factor of this one is x plus 2. Factor of this one's x minus 1. Factor of this one is x minus 3. So we could factor this whole thing. I could do that work, but it turns out that I can just look at the graph, and there it is. So this is basically the same thing. This would be y equals. Now I'd have to check my a value. This is a nice point, 6. So I put in 0. I get 2, -1, -3. 2 times -1 times -3 is 6. So it turns out the a value is 1, and the constant value up front is 1, which we can also see there. So this is just x plus 2, x minus 1, x minus 3. That's my y equals, that's factored. Now you might not take my word for it. Let's multiply this stuff back together. X plus 2, x minus 1, x minus 3. Well, this is going to be x squared plus x minus 2, all times x minus 3. This is going to give me x cubed plus x squared minus 3x squared. Which one haven't I done now? Did that. Okay, so now this, I'm halfway through. -3x, that's that one. 2 there, minus 2x plus 6. So that's going to be x cubed. Those ones is going to give me -2x squared. That's a negative side. You can't tell that, but it is. -3x, -2x is -5x plus 6. Hey, holy camolies, look. It worked. What a coincidence. So it turns out that we can graph these things and factor them. So pull out my handy-dandy graphing calculator. Y equals, clear that out. So -x cubed plus 4x squared plus 7x minus 10. Now what we're going to do is graph it. Make sure I'm at a good zoom here, but it looks like I kind of am. So it looks like my zeros are at -2, 1, and 1, 2, 3, 4. I can also check that on my table. There we go. Table settings. Start at 0. There we go. Better table. So at 1, at -2, and 5. 1, -2, and 5. So back to my graph. 1, 5. Whoop, back to the graph. 1, 5, and -2. So -2, 1, and 5 are my zeros. So this means x plus 2, x minus 1, x minus 5. Now, what I'm going to do here is look at this part. The left arm of the graph. So if I look at the graph, the left arm is this area up here, and it is rising. The right arm of the graph down here is falling, and that means that it must be odd. The leading coefficient of this one is negative. Let's see if that actually went behind. Ha! It did. So now you're supposed to just try and investigate here. So try all those out. You get a sense of what the arms do. So that's that one. Yeah. Hopefully that makes sense. Let me know. All right, so I'm just going to keep this going. Instead of doing separate files for 7, 8, 9, 10, we're just going to go through them all together. So here we've got what happens with repeated factors. So there we have x plus 1 and x minus 3. Polynomial has two factors, one of which is repeated. So it has two distinct zeros. One of them just gets repeated twice. So which one is repeated? This one is the first factor. It only does that one once, but here it does this twice. You can think about it hitting and then going back up. So this one gets repeated. So what you could write it is like this: x plus 1 times x minus 3, that's that downwards, times x minus 3. There it is going back upwards. Now, I can show you this really well with Desmos. So I'm going to go into Desmos here and demonstrate this, I think, much better than the book can, because I can do it kind of live. So y equals let's go a times x minus b, x minus c, x minus d, and then I'm going to make all these sliders. So you can see what happens if I first set them all to different values. Make that one. Okay, so they are at different values, all three different things. Now watch what happens as I bring them closer and closer and closer together. So I'm going to take this one that's at 2 and I'm going to move it to 1. Boom, 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 1.5, closer, closer, closer. As soon as it hits 1, what happens there is it really just touches the axis and then goes back up. It's what we call tangent to the axis at that point. And again, what that means is that both of those factors have come to the same place, 1 and 1. Right? If I move them apart again, I get to see this is the thing that's moving. I can set that to whatever I want. There it's at 0.5. Or I could make it higher. It just will keep going in order through those three dots. But you can see that if I move them to the same place, the kind of x-intercept or the style of the x-intercept changes. Instead of passing through, it does that U-shaped parabola thing at that point. Hopefully that makes some sense. We're into this one. Okay, so this is this thing we call multiplicity. There's basically three different things that can happen. A multiplicity of a zero says how many times it's repeated. When we get this parabolic sort of thing, that means multiplicity. Well, we will get to what multiplicity it means. And we also have this thing which is called a point of inflection. And again, those of you who are in my AP group, since we've done some calculus, you'll recognize that these are calculus terms. A point of inflection means that it changed its concavity. Concavity is the curvature. So this is a positive concavity. This is a negative concavity. Smiley or a frowny graph. And a point of inflection is when a graph goes from smiley to frowny, or vice versa. So that would be the POI, or point of inflection. So if I graph this thing, I'm going to see this, and So I'm just going to graph this thing. Actually, I'll just do it. No, I'll do it on your calculator. We'll make it look like the ones that you guys get to see. Although you can use Desmos, just not on tests. But I'm going to put this thing in its factored form. I don't even need to use the expanded form. X plus 1, close bracket. X minus 2, close bracket. This one's cubed. And this one back here was squared. Okay, so I graph it. I don't know what I've got going on there with my y value. Let's go zoom standard here. Make sure that my window's kind of nice looking to see this thing at. Oh, actually, no, I need to stretch out my window. You can see the window they want me to use from -5 to 5. Window settings, -5, 5, -100, and 100. And now I can see it a little more clearly. So you can see that it has all three types here. So its first zero is at -3. Its multiplicity is 1, and it's a linear thing. It passes right through. The next zero is at -1. Its multiplicity 2, because it got repeated twice. And it is, the book wants us to use this tangent descriptor. I actually think it's a better descriptor to say it's a quadratic descriptor. It looks like a parabola at that point. Oh, I went and shrunk down my graphing calculator. There we go. Move it over. And my last zero is at +2. It's a multiplicity 3. And it is what we call that point of inflection. But I would rather just call it a cubic sort of style of zero. So the degree of this thing is, we look back to the original, 6th degree. See? Highest coefficient. So that's my 6th degree. And if I add up all the multiplicities, 1 plus 2 plus 3, also 6. Ha ha. Ha 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 ha. Anyway, now I can graph this thing. Y equals, let's clear all this out. X to the 4th plus 2x cubed minus 15x squared minus 32x minus 16. Now, if you've gone through these things in order, instead of the way I usually teach it, you might at this point be saying, why on earth have I been doing these by hand? So you can look at this and basically have it factored. So, do I want to sketch that? Sure, I will sketch it. I know I didn't on that last one, but you can. Rewind the video and sketch it yourself. Okay, anywho, it has 3 zeros. The first zero is at -4. What did I do there? That's so weird. Okay, first zero is at -4. Multiplicity is 1 because it passes right through. Again, use whatever descriptor you want. I like linear. My next one is at -1. Multiplicity is 2 because I see it does that twisty thing. I'm going to call that quadratic instead of tangent to the x-axis, which I could also say. That's also true. And then at +4, multiplicity 1.
Mr. Castrioni, please call an immediate.
All right, sorry about that. I didn't hit my pause in time, so you are stuck listening to all of the carryovers. Anyway, the degree is, this one is 4. Some of the multiplicities is also 4. The factored form is x plus 4, which is x minus -4. X plus, actually let's go x minus 4 for this next one, because they want me to write my last one last. That's also to the first. And then x plus 1, that one has to be squared because it has to match the multiplicity. And that's that. So another couple minutes. Hopefully that makes sense. Try them out and rock and roll. All right, so carrying on here, we're now into number 9. It's again dealing with odd multiplicities. So I'm going to just try some different multiplicities here. So I pop this up here. Y equals, screw this. Skip it is what I meant to say. Skip. So what I'm going to do here is I'm just going to do this. Let's actually just clear out all these. And we're going to go y equals x minus 2 to the exponent of n. And then I'm going to add in a slider. This will allow me to do this a little more quickly. So there's my place that I'm kind of going to be focusing on. And back up a little bit, go back to my home scale. So now what we're going to do is go till 3. So it's got that point of inflection thing, or that little curve like that, right? Watch what happens if I crank this up to 5 now. It looks basically the same. It's a little bit steeper, perhaps. How about 7? Again, basically the same. A little bit flatter in the middle here. And then a little steeper on the edges. What if it went 9? Again, a little flatter, a little steeper. 11. 101st. They're all basically the same, although again, it gets squarer the larger the exponent we put in. But overall, they all fit that same general pattern. Now you can see that that's different than a linear function. If it's linear, it just goes straight through. It doesn't stop. If it's cubic or fifth or seventh or whatever, it literally goes horizontal in that middle there. And that's an important distinction. Okay, so as we graph these, they just get increasingly flat and steep. But basically, they all look the same. Hopefully that makes sense. The same thing is true of my even multiplicities. So back to my Desmos, so I can go through this more quickly. If we make this 2 instead, boop, there it is, a happy little quadratic thing. How about 4? Huh. Basically the same thing. Again, a little bit flatter in the middle, but basically the same thing. How about 6th? Huh? How about 8th? How about 10th? Basically the same thing. Again, they just get a little flatter every time. But other than that, they're basically the same. In fact, watch this. I can graph a whole bunch of them together. Paste. Minus. There you go. Minus 2. No, not there. In the exponent. There we go. Minus 2. What? Oh, I bet you I need to put brackets around my exponent. That'll do it. That'll do, donkey. So now I'm seeing 2 at the same time, right? So if I look at like 10 versus like 4, the blue is the parabolic, the black is the 4th degree. And again, you can tell that they're really not that different. If we look at the 6, they're even closer. So if you match the one with the one below it, they don't change all that much. They get a little bit flatter and a little bit steeper, but other than that, not much. So this is going to look like this. I didn't actually make it there, but let's try that again. Nudge that down. So the 4th is going to look a little bit more like that. The 6th is going to be, again, steeper, flatter, steeper. And they would all cross each other somewhere up there. Anyway. So this is what we get with the different things. Evens are tangent. Odds are that point of inflection or cubic. So the style that we really have are from, basically we can't really say it's a squared thing or a multiplicity 2 thing. We can say it's even and odd. That's all we can really say. So linear, again, is separate. This is an even, and that's a linear. So this could be 1, 2, 3, 4 degree, but it could be also 1, 2, 3, 4, 5, 6 degree. Does that make sense? Anyway, I think this is what we're trying to get at here. In each case, state the number of distinct zeros and the possible multiplicities. So if we were going to do this one, it has 2 distinct zeros. 1, 2. 2 unique zeros is another word for that instead of distinct. Speaking of which, here's my favorite teacher joke. How do you catch a unique rabbit? Ready? Unique up on it. Anyway, I love it. You guys are probably laughing at home. I'm sure you are. But the best part is the follow-up joke, which is how do you catch a tame rabbit? And those of you who've already heard this joke are stuck listening to it again. But it's still great. Well, it's the tame way. Unique up on it. Baha. Anyway, I'm not going to write these things down here. I'm just going to write it right up here. This is an even degree, so it could be multiplicity 2, 4, 6, etc. And this is an odd degree, so it could be 3, 5, 7, etc. It couldn't be degree 1, because degree 1 just passes straight through. It doesn't stop and hang out like this one does. So this must be degree 1, this must be degree 1, this could be 2, 4, 6, etc. This is what do they want? Total degree, possible multiplicities. So this has 2 distinct zeros, or unique zeros. This has 3 distinct zeros. This one has 1, 2, 3 distinct zeros. And its distinct zeros. This is an even multiplicity, 2, 4, 6, 8, etc. Even, 2, 4, 6, 8, etc. And this is linear, which means must be 1. Linear, linear, odd. Oh, I guess I can just use an O for odd. I'll write the there we go, odd. And again, this is 1, 1, this is 3, 5, 7, etc., etc., etc. Which graph could represent a polynomial of degree 8? Well, 8 has to be overall even. So this is odd because they start and end in opposite places. This is the only one that's even. So if we look at it, for this to be degree 8, this particular 0 here would have to be a 6. And hey, it might be. So what was that, B or 2? 2. Which graph has a leading coefficient that's positive? Your right arm will always tell you whether the leading coefficient is positive or not. So graph 3 and graph 4 have even positives. I, or IV. Without making a graphing calculator rough sketch. Anyway, 4th degree at 1. It's going to be at x minus 4 and at 0. And it has to have a negative lead coefficient. So it's going to go down here somewhere. This one's a linear, so it's going to come through here. This one is even, so it's going to do the even thing, and then that's linear. So it ought to look something like that. Again, depending that the highs and lows there are going to vary depending on whatever it's depending on what my scale is, right? So I can make those highs and lows higher and or lower depending on my scale. X minus 4, graph And look, it's almost like we know what we're talking about. Although again, we're zoomed in a little close here. Let's go zoom standard. Now we might be able to see it more effectively. So that looks pretty good. Did I square one of those? I swear one of these was supposed to be. Apparently it doesn't look that good. But that's just because apparently I didn't think to put that fourth power up there. Let's check again. Yeah, and again, getting my calculator to the right window settings is going to be a little goofy. If I zoom way in on this, let's go zoom decimals, try that, see if that gets me what I need to see. Yeah, I mean, I can see this little hump is small, and there's a bigger hump here. Anyway. Verified. For these ones, all I'm going to do is just write it the minimum possible degree. My favorite way of doing degree is by checking the directions. 1, 2, 3, 4 directions. It also has 4 x-intercepts, although that's not always the case. This is 3 changes at this point. This is 3 at this point. So overall, I'm going to say 6. If I was counting directions again, I'd go, okay, 1 direction, it goes back up here for a second. I can't actually see it. 2, 3 directions, 4 directions, 5 directions, 6 directions. On this, sketch it. Positive leading coefficient, so it has to go like this. 1 of multiplicity 1, so let's just go like that. 1 at 2. 2 real zeros of 2, something like that. And then 1 of 5. There we go. Negative lead coefficient. 2 zeros of 1. 1, 2. 1 at 3. And 1 of 4. There we go. Now again, there's an infinite number of solutions to that. Non-real zeros. You'll get this if you graph some things that don't graph or don't factor all the way into nice regions. Anyway, basically the number of non-real zeros is the difference between a function's degree and the number of its x-intercepts. So this would be 1, 2, 3, but it only has 1 x-intercept, so it has 2 unreal or non-real. This is 1, 2, 3, 4, but it only has 2 zeros, so 2 non-real. This would be 1, 2, 3, and it only has 1, so again, 2 non-real. This is 1, 2, 3, 4, 5, 6, and it has 1, 2, 3, but this is actually multiplicity 2, so 2 non-real as well, because it has 6 potential 4 reals. 1, 2, 3, 4. Anyway, that's again kind of beyond the scope of the course, but it's cool nonetheless. All right, and then this one is our final one of these, final polynomial piece. And so we've got leading coefficients other than 1. Remember we talked about that unique factorization theorem that says everything can be written as a number of their factors. And this thing we can think about as being a vertical stretch, because there are really an infinite number of graphs that will go through the same x-intercepts. They'll just have different vertical stretches. And the vertical stretch will not affect the intercepts. So here's a third degree polynomial. It has integral or integer x-intercepts and passes through the point 2, negative 24. So I can initially just go, okay, x plus 1, x minus 3. That's what I can see right now straight out. Now, that's it. But there's actually going to be a lot of different graphs that can do that. We want the specific one that goes through here. So what we're going to do is we're going to put that point in, just like we've done in many other courses to date. 2 for that. 2 plus 1 there, and 2 minus 3 here. This is negative 24. This is c times 2 plus, 2 times 3 is 6, times negative 1 is negative 6. So negative 6c equals negative 24, or c equals 4, if I just divide both sides by negative 6. So there's my c value. So my final answer would be y equals 4x, x plus 1, x minus 3. And I know they wanted me to write it in expanded form. I just don't want to. Factored form is better anyway. Leaving it there, good. Graph represents a polynomial of the lowest possible degree. They have to tell us lowest possible degree because this might be a degree 3 multiplicity. It looks like it, but hey, it could have been 5 or 7 or 9 or 311 or 3011. Who knows? Any of those things. So we'll assume it's the lowest possible degree. That means that that's 3. So x plus 2 cubed, x minus 2 to the first, because that is a linear pass-through. So multiplicity 1. Now, I don't have my a value yet, or my c value. I like writing it as an a, because I like the vertical stretch thing. And you go up here and go, negative 2! Nice! Except that you're wrong. Because the scale here is to 20, and there are 5 things, so they're all 4. 4, 8, 12, 16, 20. So this is really negative 8, according to the scale. So now I put in the point 0, negative 8. They don't have to tell me a point. It has to be clear, but they don't have to say it. As long as they say that all the intercepts are integers, then I can read that and go, okay, it goes through 0, negative 8. So negative 8 equals a times 0 plus 2 cubed, 0 minus 2. Well, 2 cubed is 8 times negative 2 is negative 16. Negative 8 equals a times negative 16. A equals 1/2. Bada bing, bada boom. So there we go, all done. Now, another thing that's really handy to do is to check. This is opening up, so it should have a positive a value. Did I get a positive a value? Yes. Yes, I did. You could also type the whole thing into your calculator, right? And just see, did it work? And it should. Fourth degree polynomial passes through 1, negative 12 and is tangent to the axis. Again, I got to remember what that means. Tangent to the axis means it does one of these things. Where's 1, negative 12? Over here somewhere. And it has a 0 here and here, so it has to do something like that. So, y equals a x minus 2 squared x plus 3 squared. Put in the point negative 12, 1. A times, this is just going to be 1. 4 squared is 16. Negative 12. So a equals negative 12 sixteenths, or negative 3/4. And that makes sense based on the way I drew it. It does all of that. And if I really wanted to be extra sure, I could graph it. I can double check myself, triple check myself with my calculator, so I'm absolutely sure without a shadow of a doubt that I've done it correctly. If I'm putting this in like this, I like putting the whole thing in brackets. So there's that. X minus 2 squared x minus, nope, plus 3. Look at me go. Plus 3. And that's again all squared. Be careful writing those things in. That's important. Anywho, there is my graph. And now if I really wanted to, I know it goes to the point 1, negative 12. Let's check the table. 1, negative 12. I did it. All right. Fourth degree polynomial passes through this. This is when I have non-rational zeros. Now, there's 2 ways I could actually write this. The first way I could do it is just the same way we've been doing. X plus 1, x minus 3/2, and x minus 2. Okay? Fourth degree polynomial, so I've got 4, 1, 2, 3, 4. They all have to be linear. and it passes to the point 1, comma 2. So y equals a times all that. So now I'd go 2 equals a times 1. 1 plus 1 is 2. 1 minus 3/2 is negative 1/2. And 1 minus 2 is negative 1. So I multiply all that together. That cancels to negative 1. That negative 1 makes it positive 1. So I just get a equals 2. Cool. So I could write this like this. 2x, x plus 1, x minus 3/2, x minus 2. Or I could also distribute this 2 into here to get rid of my fraction if I didn't want my fraction. This is no more correct than the other way. Both of those are absolutely fine. Sometimes the question might want this. Sometimes the question might want this. You should be fluid enough to go back and forth. Polynomial has the following 3 roots. -2. And so it's going to be x plus 2, multiplicity 1. Now, I could look at this off the front of my hat and go, okay, that's just x minus the third. Or I could go, hey, that's 3x minus 1 squared. And x minus 1 cubed. Corresponding polynomial has y-intercept of 2/3. Give it using only integral factors. So I've done that. I've already got that as an integral factor from this. And then what I can do is go y equals a. And then all I have to do is put in the point 2/3 equals a times 2 -1 squared, -1 cubed. So -1 squared is 1, -1 cubed is still -1, so -2. A equals -1/3. So that would work. I could do that way. Anyway, that is it. That's all of those. That's all those lessons. Try them out. My guess is that they made sense after about the first thing, after we did that multiplicity piece. But if there's anything you're struggling with, let me know. Have a fantastic rest of your day, whatever day you're doing this, and or night, but enjoy.